Welcome to this explainer. Today, we're diving into something that is, frankly, incredibly tiny, deceptively simple, but absolutely foundational to the world around us. We're talking about the diode. It's basically this microscopic gatekeeper that literally built the entire electronic age. Seriously, if you just take a second and look around the room you're in right now, you are likely surrounded by thousands, maybe even millions of them, just working silently to keep your modern life running. Okay, let's dive into this. At its absolute core, a diode is simply a one-way street for electricity. That's it. But this single, surprisingly powerful concept, well, it's the absolute foundation of every single phone in your pocket, every laptop sitting on your desk, and every LED bulb glowing above your head right now. Every single one of them depends on this exact mechanism to function.
But you know what's truly fascinating, and honestly deeply ironic, is how all of this actually started. Because this indestructible, microscopic device that runs our ultra-modern smartphones today, it did not begin in some pristine, high-tech, multi-billion-dollar laboratory. No way. It actually started as a really frustrating, incredibly annoying glitch way back in 1880. It was just this weird, totally useless black stain forming inside Thomas Edison's glass light bulbs.
So to see exactly how we got from that annoying stain to the modern digital age, we're going to follow this timeline. We'll start right there in 1880 with the Edison effect, then move forward to Fleming's working valve in 1904, we'll explore some crystal physics in the 1930s, and finally we'll arrive at the massive 1945 Bell Labs breakthrough.
Section 1. The Accidental Discovery, Edison's Light Bulb Glitch.
So picture this. It's 1880, and Edison is desperately trying to figure out why his glowing light bulb filaments keep darkening the glass near the positive end. It was completely ruining the lifespan of his bulbs. So to figure it out, he runs kind of an odd experiment. He actually sealed a small metal plate inside the glass bulb, just hovering there right near the filament, but importantly, not touching it. And amazingly, when he hooked that plate up to the positive side of the circuit, a tiny current mysteriously jumped right across the empty vacuum to the plate. But, and here's the kicker, when he hooked it up to the negative side, absolutely zero current flowed. Without even realizing it, Edison had accidentally built the world's first diode. But, rather than changing the world right then and there, he just saw a solution without a problem. He went ahead and patented it in 1883 as the Edison effect, and then basically just walked away from it. He completely dismissed it as a useless scientific curiosity while he went off to chase, more profitable inventions.
Moving on to Section 2. Fleming's oscillation valve, finding a purpose.
Yeah, what's really interesting about this slide is the concept called rectification. This is the absolute key to everything. In 1904, a British physicist named John Ambrose Fleming, who actually used to consult for Edison, by the way, was working on early radio technology, and he had a massive problem on his hands. You see, early radio signals came in as alternating current, meaning they violently oscillated back and forth. But to actually detect that signal and, turn it into sound you could actually hear, the radio receiver desperately needed a steady current flowing in just one single direction. And that's when Fleming remembered Edison's weird little light bulb trick. He suddenly realized that a heated filament and a metal plate inside a vacuum could act exactly like a valve in a water pipe. It would block the backward flow and let only the forward flow through. By doing this, he successfully achieved rectification, taking physics straight out of the textbook and turning it into working, real-world electronics. Fleming called his invention the oscillation valve, but we know it today as the vacuum tube diode, and for decades this thing was the absolute beating heart of every single radio on Earth. But of course, there was a catch. Vacuum tubes were, at the end of the day, essentially just heavily modified light bulbs. That meant they were made of fragile glass, they got extremely dangerously hot, and they consumed just massive amounts of power just to heat up that filament. And predictably, because it's basically a light bulb, they burned out all the time. Which brings us to Section 3, the crystal alternative, from glass to rocks. Okay, so long before Fleming's vacuum tubes, way back in 1874, a physicist named Carl Ferdinand Braun noticed something absolutely wild about lead sulfide crystals, which are also known as galena. Fast forward a bit, an early radio hobbyist actually took this completely obscure discovery and ran with it, building what they lovingly called cat's whisker detectors. Basically, they took a literal lump of this galena crystal and they would delicately poke the surface with a super fine metal wire. And almost magically, if they hit just the right contact point, the crystal itself would rectify the radio signal on its own. It was incredible. It needed zero batteries, there was no heated filament to burn out, and it was unbelievably cheap. But There was a pretty huge downside. It was terribly, terribly finicky. I mean, you had to constantly poke around the rock just to find that one magic spot, and the delicate wire could be knocked completely out of alignment just because someone, say, walked a little too heavily on the floorboards in the very next room.
So, Section 4, Engineering the PN Junction, Bell Labs in World War II. Up to this point, we had a glass tube that constantly burned out and a literal rock that fell apart if you walked too heavily nearby. Enter World War II and the absolutely incredible engineering of the PN junction.
During the war, the military desperately needed highly reliable radar systems, and that meant they needed reliable rectifiers, ones that didn't rely on shattering glass or those finicky little cat whiskers. This massive, urgent push led researchers to finally look really deep inside the actual quantum physics of these crystals. And what they did was perfect a fascinating chemical process called doping. Through doping, they deliberately added these tiny, hyper-controlled chemical impurities right into the semiconductor crystals. Doing this fundamentally altered how electricity behaved inside the rock itself. It was a total game changer. So here is the exact microscopic recipe they discovered. First, you dope one side of a silicon crystal so it has all these extra free electrons. We call this the N-type side. Then, you dope another piece so it's actually missing electrons, creating what we call holes. This is the P-type side. It helps to think of the electrons as cars and the holes as empty parking spaces. When you finally fuse these two sides together to create a PN junction, they form this tiny, microscopic boundary right in the middle called the depletion zone. And just like that, this clever little sandwich effectively replaced those massive, hot, glowing glass tubes forever, swapping them out for a silent, microscopic sliver of engineered crystal.
And this brilliantly illustrates exactly how the magic happens. When you push electricity in the right direction, which is called forward bias, that depletion zone gate simply opens up. The cars and the parking spaces naturally move toward each other, and the electrical current just easily passes right through the crystal. But look what happens when you try to push the current the wrong way, into reverse bias. The gate literally slams shut. The depletion zone instantly widens out, acting as a solid physical barrier, and almost zero current can flow. Which of course brings us to the ultimate question. We've just seen exactly how to build this tiny, completely silent one-way gate. But why does a one-way street for electricity actually matter so much to you and me? Like, what's the big deal?
That takes us to Section 5, Powering the Modern World, from chargers to solar panels. Let's see exactly what this tiny little gatekeeper unlocks for us.
Let's move to and see how this builds our modern reality. Take your standard phone charger, for example. That little block is absolutely packed with diodes, actively rectifying that messy, oscillating wall power into smooth, steady battery power. Or how about the lights in your house? LED literally stands for light-emitting diode. They are just PN junctions engineered to efficiently release photons of light instead of wasting all that energy as heat. And what about solar panels? Well, they are essentially just giant diodes running in reverse. Instead of using electricity to create light, the sun's light knocks electrons loose, and that diode gate channels the resultant current straight into your home. Plus, practically every single circuit board on the planet uses diodes as these protective one-way valves. They make absolutely sure that a sudden, unexpected backward surge of current doesn't just immediately fry all your expensive components. So the crucial point is this. We've gone from an incredibly hot, incredibly fragile energy-wasting glass bulb that Thomas Edison literally couldn't even find a use for, to an indestructible sliver of engineered crystal that is smaller than a single grain of rice. It has zero moving parts, there's no vacuum to maintain, and absolutely no heated filament to burn out. And yet these microscopic gatekeepers are working away right now by the absolute billions, silently directing the flow of electrons to make our entire modern world possible. It's a remarkably simple idea, but with massive, world-changing consequences. Before we wrap up, I want to leave you with one final, fascinating thought. If the invention of a single, simple, one-way gate built the entire foundation of modern electronics, what on earth do you think happened when scientists finally figured out how to add a second gate, giving birth to the transistor? Well, let me tell you, that is an even wilder story. Thank you so much for exploring this with me today, and I absolutely cannot wait to dive into that next chapter with you soon.